Namaste. I, Jv'n Neha Sharma, JVWU Women's University, Department of Science and Technology, Faculty of Education and Methodology. So our today's topic is Introduction of Gradient Descent Algorithm. Right? So, as in previous lecture, we studied about the activation function, cost function, learning rate, right? So now here we studied gradient descent algorithm. Okay, so why do we need gradient descent algorithm? So consider the three-dimensional graph below in the context of cost function. Our goal is to move the mountain, okay, in the top right corner to the dark blue sea in the bottom left. Okay, dark blue sea in the bottom left. Okay. So here the arrow represents what? This arrow represents what? So this arrow represents the direction of the steepest descent, means negative gradient. From any given point, the direction that decreases the cost function as quickly as possible. And starting at the top of the mountain, we take our first step downhill in the direction specified by the negative gradient. Next, we recalculate the negative gradient and take another step in direction it's specified. We continue this process again and again until we get to the bottom of the graph or the point where we can no longer move downhill a local minimum. So basically the target of gradient descendant is to find, right, either global minima or global maximum. If अगर हमारा पॉजिटिव है तो ग्लोबल मैक्सिमा, नेगेटिव है तो ग्लोबल मिनिमम. Okay, so again, we take here the example of the mountain. So if you wanna reach on the top of the mountain, so you started from the bottom, right? So if you go uh, in like in this function, either you go in this function. So it all depends on the mountain, right? So how far you get your point, in how much time you get your point. So it depends on the height of the mountain. So there are many different hyperparameters of the parameters in different situations with different hills. Here we take example of mountain. So it depends on the shape of the mountain, height of the mountain, width of the mountain, and many different parameters also, right? So gradient descent problem is to find the global minima or maximum. Okay, and also decrease the loss function and enhance the performance of the model. Okay, so here first is training a neural network. For any kind, in any kind of neural network, you first have to train the model, right? Like for example, if you if you wanna do some programming or coding, you just first need to learn that coding. Likewise here, this model also have to learn, right? So so the models are trained by any algorithm, right? So gradient descendant algorithm is one of them. So how to train the neural network in gradient descendant? As you probably already know, a neural network is composed of neurons, right? Here an input layer, hidden layers, output layers. Each neuron is actually a sum of all its input, which are in fact of the output from the previous layer multiplied by the multiplied by the weight associated with it. An additional term bias is also added to this sum, and the nonlinear function known as activation function is applied to this result. And here you see the function. So basically, if you see here, first there are the inputs x1, x2, x1 and the weight associated with that. So we calculate x1 w1 plus x2 w2 plus xn wn, right? Then this goes here, the result goes here. Now we add bias on this to enhance the performance of the system. Then we add here the activation function, which we are also studied in previous lectures, to improvise the performance of the model and minimize the error and the loss function, right? So here in the final we got what f of e plus definition of I equal to 1 to n f by w. Okay. So parameter initializations are also very important in training the model, because initially we have to initialize the parameters like uh, for example, we take the example of hill. So height of the hill, width of the hill, shape of the hill, longitude, and many other different parameters. So all these parameters are set initially, and all these parameters are known as hypermeters, hyperparameters, because in this, like, you have to set weight, bias, learning rate, input, prediction, predictive output, right? So to calculate the error. Okay, so these parameters are exactly numerical values that we will try to adjust by training the network with already labeled data set. As in any other supervised machine learning problem, the final result will be the model built from the data and able to make predictions over future samples. Okay, so parameter initialization we do first. So initialize the weight randomly in order to help our network and taking it symmetry. If here we use w equal to 0, then what can happen? Nothing. No use of this kind of algorithm and all thing. It gives you the same output, right? And it gives you the straight line. So we have to take the weight randomly in order to help our network, breaking the symmetry. Our goal is to prevent all neurons in a layer from learning the same thing. The weight for each layer are usually generated using a normal distribution of 0, means 1 upon n, 2 upon n, varies different variances, and it all depends on the your model, right? What you want to predict. So this value for the variance depend on the activation function. And in gradient descendant algorithm, we also use the rectified linear unit activation function. Okay, so initialize the bias to 0. From here, we will proceed iteratively by following the optimization, because gradient descendant is the optimization algorithm that will try to minimize the difference between the actual output and the estimated, or to say desired output. Okay, so gradient descent is our most used algorithm to train the neural network in gradient descendant. What's this gradient? We will define it later, but for now, hold to the following idea that the gradient is a numerical calculation allowing us to know how to adjust parameters in the network to get our desired output in minimum derivation, because if derivation goes on, then also computation goes on, then the time complexity increases and the performance of the model decreases, right? So basically gradient descendant have different type in which we have to process our data, or to say train our data. So there are three type of gradient descent: batch gradient descent, stochastic, and the mini batch gradient descent. So in batch, all the available training data injected at once in the system, right? You don't need to inject again and again. You just put whole data set from the CSV file and upload it or import it to the model. Okay. So so here the performance is very weak, because we just import all the data at once, and it implies the higher risk of getting stuck. And gradient will be calculated using all the samples, variations will be minimal, later or sooner, right? So general rule for a neural network, it also is it always positive, because if it goes with negative, then of course performance shattered, right? Performance goes in negative. Okay, so input with some randomness, right? So batch gradient algorithm is take longer time, because it has to average of all the get average of all the training sample as a gradient, and it have to calculate again and again and again. So this one not as a great approach. So next one is stochastic gradient. Stochastic gradient is a random sample in which the gradient is calculated for the specific sample only, and implying the introduction of the desired randomness. So we randomly take the data and impose it to the system and then calculate the gradient over it. So this the main problem with this version is slowness because it need more and more iteration, right? Additionally, it doesn't take advantage of available computing resources. So using gradient after each training data sample instead of computing sample faster for the batch mode. Faster, but performance is still stuck here also because you need to again and again get the random data and calculate the gradient over that. Okay, the third one is mini batch gradient. This one is majorly used because and this you what you do is you you distribute the data in mini batches and then import these mini batches into the model, right? So the random items are introduced in each iteration है ना. तो for loop चला दिया जैसे then हर for loop पे एक batch जाएगा. ठीक है, तो if this preserve the advantages of the second version and also it getting faster training due to the parallelization of the operation. So we will use this version of an algorithm gradient descent and we use generally this kind of mini batch approach in majorly most of the models of the deep learning and the machine learning. Okay, so because it enhances the performance, it creates a good balance between the randomness and the training time and not too large for the available memory. So this is the graph. You can see gradient descendant, stochastic. Here GD is gradient descendant, simple one. Then this is stochastic, and this is the batch size or mini batches. You can see here the performance. So like this one is gradient descent. It's good, but with the mini batches like batch size 100, 10, right? So it goes with different mini batch sizes. Okay. So stochastic gradient descendant. So this one is the batch one, division. So you can see here the performance is very poor. Then stochastic, okay, it do better, and in batch sizes it goes down, right? So mini batch sizes is the updated approach for the gradient descendant in most of the models. And here we also use this kind of approach in gradient descent algorithm. So this algorithm using the mini batch gradient descent method, and we introduce a mini batch input with and random samples from all previously labeled training data set. Like if, for example, I have a data set of 100, so I divide the data set of 100 into 10 mini batches with the size of 10 each. Okay, so we have the actual output, and after the appropriate calculation on each layer of the network, we obtain the predictions at the output. So this step is forward propagation. So always we need to first traverse the data from left to right. Okay, so this is what forward propagation of data or to say feed forward network. Okay, then in step 3, we evaluate the loss function for the mini batch. It's only a previously chosen mathematical function based on our specific problem time. So this is also depend on your problem which kind of loss function you choose, right? And loss function is basically used to improvise the model and minimize the error. Okay, and used to evaluate the difference between the predictions of our network, basically error, or is the difference between the actual output and the desired output. So in a proper way, the value of this loss function is the number of the algorithm is trying to minimize, and the following steps are oriented towards this. So we calculate the gradient at the multivariable derivative of the loss function with respect to all the network parameters. So gradient is nothing but the derivative. Okay, you have to calculate the derivative. Okay, in each for each batch, and then it goes on with different parameters, and then adding all of these gradients, right? So basically, practically it would be the slope of the tangent line to loss function and the current one, right? So mathematically, it's a vector that gives us a direction in which the loss function increases faster. So we should move in opposite direction. If we try to minimize it, we need to go to opposite direction. So basically, this is the concept of gradient, and we calculate the gradient. Okay, so we calculate gradients like for different problems. We use different loss functions, different activation function, and output are also different according to the problem. Okay, so how can we measure the true impact of first layer parameter variation on the final loss, knowing the changes affected all neurons in successive layer two? The answer is backpropagation. So backpropagation algorithm uh, really gave good performance here because without backpropagation gradient design cannot work properly because gradient descent works on the backend of gradient descent is basically backpropagation. So this algorithm starts by calculating the partial derivatives of the loss function with respect to the parameters of the last year. Then it goes on, and on, which don't influence over any other network parameters because of backpropagation. So it is not become complicated. Otherwise, it don't give you answer. It hamper your performance, and the model is crashed. So in backend of the gradient descent, backpropagation algorithm work really well to uh, to save your model with bad performance, or to say to is really stuck. If the whole network goes stuck if the backpropagation not working in behind of the gradient descent, because you need to calculate the derivative in each and every with each and every layer, right? With different parameters. So it also influence the other layers, right? So so if you don't wanna make this happen, so you need back propagation here to change all the neural network in successive layer two, right? So this by the use of back propagation, this is not become complicated and gradient design work really well with the system, right? And in previous lecture, there's a problem vanishing gradient, right? So this is also connecting with this algorithm. So in vanishing gradient, the slope is too small. The learning rate slope is too small, and there are another problem is vanishing exploding. Vanishing exploding, the learning rate slope is too large. Okay, so vanishing descent problem is resolved by ReLU, and it present in the sigmoid and tangent function, but it is resolved in ReLU. Uh, okay, so this is all about it. Thank you so much.